Good evening to all of you. Good evening to Jeannette Heiligers, our speaker of this evening. I will introduce you in a few moments. Today was a very sunny day, and when I cycled to the university, I tried to imagine that I cycled against the sun, that I had some solar winds against my nose. It was very, very difficult to experience, and I read this afternoon that it's for a human being on this planet, it's impossible to experience this very soft forces. But when you're in space, and when you're very, very lightweight, and you have a very huge sail, you can feel the solar pressure, the solar winds getting you somewhere. Jeannette Heiligers, she is an assistant professor in astrodynamics and space missions at the Technical University in Delft, specialized in solar sailing, and she will answer the question, how do you sail on a solar wind? What happens to the photons? She will talk about several very intriguing applications of solar sailing. She's working on a project called SWEEP. That's a space vacuum cleaner, a space duster, which can be used to remove debris. There's a lot of debris circling around our planet, harming satellites, perhaps even the astronauts in the International Space Station. So that's a really big problem. But Jeannette is working on a light, sun-driven space duster. That's what she's going to talk about. In the end of the talk, she will also talk about climate engineering, because the solar sails can also be used to shield off the sun a little bit. That's at the end of your topic. Yep. First, you're going to talk about the solar sails. What are they? How do they work? What can you do with it? So yep. I want a big hand for Jeannette Heiligers.
Thank you very much for the introduction, and thank you very much for inviting me here tonight. It's an honor to stand in front of such a big audience. I wasn't expecting that, so absolutely wonderful to see you all here today and giving me an opportunity to talk about what I'm passionate about, what my research, my education, my everyday work life is about, which is indeed solar sailing. But before I start my story, maybe indeed a little bit about my background. So I graduated in 2008 from Delft University of Technology, the Faculty of Aerospace Engineering. I did a master's in space engineering, and after graduating I moved to Glasgow in Scotland for a PhD, under the supervision of one of the big names in solar sailing, Professor Colin McInnes. And he made me excited about this wonderful, elegant, beautiful technology. After I completed my PhD, I stayed in Glasgow for a few years for my first postdoc. And then I got a nice grant from the European Union, which took me to the University of Colorado in Boulder for about a year and a half, 2 years. And then the last part of that fellowship was back. The circle was full. I returned to Delft, where I am now still as indeed an assistant professor. So that's a little bit about myself. What we will be talking about today? Oh, I hit this slide in a previous version, but apparently it's here. I've been lucky to have traveled quite a bit for conferences and also for just leisure, personal holidays. But one of the absolute highlights for me, and if you ever do have a chance, was to see an actual space shuttle in a museum close to Washington Airport. And if I would not have been excited about space engineering already, that for sure would have made me even more excited. But that's about me. So what will we be talking about today? So today, for those of you who are maybe not that familiar with astrodynamics or the motion of satellites in space, I will start with a very short introduction on satellite orbits and why a satellite needs propulsion, for example, a solar sail or any form of propulsion. I'll then talk about what is a solar sail, how does it work, what are its pros and cons, and also a bit of a historical perspective. So Is it sci-fi, or is it something that's been around already for hundreds of years? After that, we'll have a short break and for questions, if you like. So that kind of concludes more than the technical part of the presentation. And after questions, I'll then focus on some applications of solar sails, how solar sails can help contribute to providing solutions to big challenges that society is facing. But let me first give a very brief introduction into satellite orbits. Well, satellites in themselves, you're all familiar with it. It's something that we can't do without. Before you leave your house in the morning to go to work or school or wherever you go, you've already used dozens of satellites, whether it's to check the weather, to check the news, whether you eat your cereal or your bread that has been farmed with precision farming, for which we use satellites. There are really dozens and dozens of applications of satellites. And these satellites, they all move around the Earth, or they kind of hover maybe above the Earth. Well, they don't actually hover above the Earth, because if they would remain still above the Earth, the gravity would pull the satellite down, and the satellite would crash on Earth. So how to prevent that? Well, when a satellite is launched into space, the rocket gives it a certain speed. But the magnitude of that speed, the magnitude of that velocity is very important. If it's too slow, too small, satellite does not have enough velocity and it will still crash on Earth. If it's too big, the satellite might even escape from Earth. Only when you get it just right, the satellite will nicely follow a closed orbit around the Earth. And the velocity that you need for that is basically the centrifugal force. So mass times velocity squared divided by the radius, where the radius is the distance between the center of the Earth and the satellite. You can compare this to, I think it's called hammer throwing in English, where you kind of swing a hammer around, where kind of the tension in the cord is equal to the centrifugal force. Here it's a bit easier to understand because there's a physical connection between the object, the hammer, and the person, while of course there's no physical connection between the Earth and the satellite, but principle is still the same. Now this is what happens if only gravity acts on the satellite, but what if more forces act on a satellite? What if a satellite has a propulsion mechanism on board? Why would it even need propulsion? Well, there are some examples. One of the maybe most obvious one is, of course, to be launched into an orbit around Earth. Propulsion is needed. A big rocket brings the satellite from the Earth's surface to an orbit around the Earth. But also, once it's in an orbit, for example, around Earth, it might need to maneuver to a different orbit, slightly different altitude, height above the Earth, maybe slightly different orientation of the orbit. Also for that, it needs some propulsion to get it from A to B. And of course, also, if we want to explore our solar system, if we want to go from Earth to a different planet, the satellite needs some propulsion to get there. Now, the traditional way of creating a propulsive force in space is through basically a rocket, where the rocket works in the way that it expels propellant from the back of the rocket. So it can be a big rocket, can also be a tiny rocket on board of a satellite, but it expels a propellant, a sort of fuel, and based on Newton's third law, the satellite or the rocket is accelerated in the opposite direction. But this is if we use fuel. But as we know on Earth, when you drive your car, when you run out of fuel, you can't propel or accelerate your vehicle anymore. It's also not a very sustainable way of moving forward. So on Earth, we've been trying to find, of course, more sustainable forms to propel vehicles, like cars or trains, using wind or water or sunlight to to produce electricity and, of course, with electric cars to drive yourself forwards. Now, in space, we don't have wind, we don't have water, but we do have a lot of sunlight. And that is exactly kind of the fuel of a solar sail-propelled satellite. A solar sail uses sunlight to drive the satellite forward to get from A to B. So what is a solar sail and how does it work? Well, for that, let me first tell you what it's composed of. So here we have the sun, and this is, let's say, the sail. We're looking edgewise onto the sail, so the sail is facing the sun. Then it's made of a substrate, basically a very thin sheet of plastic, mylar or captain. And on one side we have a very reflective coating, an aluminum coating. And on the back there is a chromium coating and a very emissive coating to release any heat that is absorbed by the solar sail to radiate it into outer space. This is what it's made up of. How does it work? Well, once photons hit the sail, you can imagine that they kind of, and I'll repeat that they kind of push the sail in this direction. So they create a force in this direction. But also when they are reflected, they kind of push back against the sail, and they also produce a force in this direction. The photons transfer their momentum to the sail, and this creates two forces, one in the direction of sunlight and one kind of perpendicular to it. And if you sum the two forces, you see that the total force on the solar sail acts more or less perpendicular to the membrane. Now, and this force can be used to maneuver a satellite from one orbit to another. So, for example, if we have a satellite in an orbit around the sun, we can equip that satellite with a solar sail. Sorry, the velocity of this satellite is in the direction of motion. We can equip the satellite with a solar sail. We then have a force acting in this direction. So part of the force acts in the direction of the velocity. So the satellite will be accelerated in that direction, and the solar sail brings the satellite to a higher orbit around the sun. Now, throughout the presentation, I have a few quiz questions just for you to think about. If you like to answer them, feel free to raise your arm or to shout. And the first question I have is, do you think it's possible to use solar sails to not only move away from the sun, but also to move to an orbit closer to the sun? It's a simple yes-no. It's not a simple question, but it's a yes-no question. So if you like to think about it for a few seconds. Anyone in favor of yes? Yes. Anyone in favor of no? Yeah, there's certainly truth to the first answer in the sense that the force always has a component away from the sun. But the answer is indeed yes, because it's not just about that the force is away from the sun. What is more important, so the answer is yes, is that instead of kind of orienting the solar sail, so we previously had the sail oriented like this, where one component of the force acts in the direction of the velocity, so it's accelerated forwards. While if we orient the sail in the opposite direction, the force partially acts against the velocity. So the satellite slows down and the gravity of the sun pulls it towards the sun, and therefore you can enter into an orbit closer to the sun. So this is a very common and understandable misconception of solar sails, that it only blows the satellite out of the solar system, but you can actually maneuver everywhere within the solar system. So this is kind of the basic principle. Then what does a solar sail look like? Well, there are different configurations. The most common one is the one you see here. So what you see here at the center is the satellite bus, the kind of the satellite itself. And after launch, these kind of booms, these 4 booms are deployed, and they pull these 4 sail quadrants out from the satellite bus. It's kind of like a big kite. But there are other forms of solar sails, for example, a disc solar sail, where instead of using booms to push the sail out, the sail is kind of wrapped around the satellite, and by spinning up the satellite, the sail automatically winds off the spacecraft bus, and it needs to keep spinning to keep the sail flat. Another type is what we call a heliogyro, or more like a helicopter solar sail, where instead of we have these big sail membranes, we divide the whole sail into very long, slender blades. And these blades each can be pitched individually, like a helicopter rotor. And this causes that this is more like a 3-dimensional solar sail, this is a 2-dimensional solar sail. And this provides some additional force capabilities, but I won't go into detail on that here. So the biggest difference is indeed in kind of storing the sail and deploying the sail. So this can be done passively, both by spinning up the sail, and the sail automatically winds off the satellite, while in this case, we need to actively push booms out of the spacecraft and pull the sail out of the spacecraft. We can now, if you like, talk a little bit more in detail about what force actually acts on a solar sail. A few equations, but hopefully, easy to follow and understandable. So before I go into the details, let me first say that we, for now, make a big assumption that the solar sail is a perfect mirror. That means it's perfectly flat, no wrinkles, no imperfections, and it's also a perfect mirror in the sense that all the photons are specularly reflected. So that means that the angle of incidence is the angle of reflectance. Now, in reality, that's not the case. In reality, in addition to specular reflection, we also have diffuse reflection. Some photons are absorbed and are re-emitted through thermal emission. But for now, I forget about all of that. I will deal with a kind of an idealistic solar sail. So then, if we have the sun here, and again here the solar sail, we're looking again edgewise onto the sail is facing the sun, then at a certain distance from the sun, on this surface acts a certain pressure, the solar radiation pressure. That's the pressure that photons exert on any object anywhere in space. Then there's my second quiz question. So what do you think? Is the solar radiation pressure on Earth, or on a satellite in orbit around Earth, but at the distance from the sun equal to that of the Earth, is it smaller, larger, or just as large as the pressure that a $1 bill or any other note exerts on your hand when you hold it flat in your hand? It's of course a very tiny pressure, right, of a bill in your hand. Do you think it's smaller, equal, or larger? Anyone in favor of smaller? Quite a few. Equal? Yeah. Larger? Yeah. So it's smaller.
It is.
So the pressure of the bill is only 1 Newton per square meter. That of solar radiation pressure is 1,000,000 times smaller. It's in the order of micronewtons per square meter. And this is important for something I'll refer to this later. So very, very tiny pressure that acts on a surface, let's say the sail area of size A. Then the force, as I said, when the photons hit the sail, kind of act in the direction in which the sunlight reaches the sail. So we have a force once the photons hit the sail of magnitude Fi. And the magnitude is nothing more than the pressure times the area. Pressure in Newton per square meter, area in square meter. As I said, when the photons are then reflected by the solar sail, they kind of push back against the sail, and they create a force, in this case in the same direction, and it's also of equal magnitude. Again, pressure times area. So the total force on the solar sail is simply 2 times the solar radiation pressure times the area of the sail. Now this is for a sail that faces the sun, so the full area is exposed to the sun, and you can capture photons with the full area, but you might want to orient it also in a different direction in order to steer the satellite in a certain direction. And then we need to take into account that the area with which you can capture and reflect photons is reduced, equal by cosine of this pitch angle alpha. So when the sail is pitched, the force magnitude drops, if you do the math, by a factor cosine alpha squared. So that means that the force is, of course, largest when the sail fully faces the sun, and it's basically 0 when you put the sail edgewise to the sun, because there's no area to capture photons with. I can demonstrate this a little bit better in a short animation. So on the top, you see a 3D animation. On the bottom, we're looking from above. And what you see is that the sail orients itself at different attitudes with respect to the incoming sunlight, and the red arrow indicates the direction and the magnitude of the force. So you indeed see that at this moment, the force is maximum because the sail faces the sun, while when it's edgewise onto the sail like this, there's no force at all. And this then also allows me to explain the pros and cons of solar sailing. But before I go into something that has to do with these forces, I want to come back to this very small solar radiation pressure and your answer as well. The solar radiation pressure is so extremely small that in order to generate any non-negligible force, you need a very large area. And that's why we're talking about 80 square meters, or maybe even bigger. I'll show you later. Then again, looking at these animations, another disadvantage of solar sailing is that you cannot produce a force in the direction of sunlight. You see that no matter how you orient the solar sail, the force always points slightly away from the sun. And in certain applications, certain missions that you might want to fly, this can be a disadvantage. And another disadvantage is that, again, the more you pitch the sail away from sun facing, the smaller the force. So the force magnitude and direction are very coupled. You don't have these disadvantages with fuel-based propulsion. A rocket can thrust in any direction. The magnitude of the force is not dependent on in which direction it thrusts. So these are really limiting characteristics of solar sailing. So you might wonder then why go through all the trouble? Well, there's one huge advantage of solar sailing, and that's that it doesn't rely on any fuel, at least not on fuel that's stored on board the satellite. The sun is the propellant source. The sun provides the fuel. So as long as the sun keeps shining, the solar sail can propel the satellite forwards. This means that you can, in theory, achieve unlimited speeds. You can achieve unlimited lifetimes of a mission. You'll never run out of propellant. The satellite never stops accelerating. And therefore, new missions become possible. And I'll talk about that later in the presentation. Now, these are the technical details. Let's now have a look at a bit of a historical perspective. Is it all sci-fi? Is it something that we already use? What is the current state of the art? Well, before I get to the current state of the art, I would like to go back quite a few hundreds of years, because the seeds of kind of solar sailing, they were created, planted, I don't know, already in the 1600s, when Kepler, a big name in astrodynamics, observed a comet Halley, He didn't know it was Comet Halley, but later it was named Comet Halley. And he saw this object in the sky, and he saw the tail, and he thought there must be some interaction between some sort of wind or some sort of, some sort of interaction between the sun and this object, this comet. So he wrote to Galileo Galilei that maybe in the future, mankind or humankind might provide ships or sails adapted to the heavenly breezes. These heavenly breezes was this interaction between the sun and the comet. And there will be some who will brave even that void, and that void was space. So he already thought that there must be some interaction that we could potentially in the future exploit to travel through space. And this idea was further kind of strengthened or enforced, or no, not enforced, but kind of enlarged, confirmed maybe, when he saw or he observed that one of the tails of the comet always points away from the sun. So he knew that for sure there must be an interaction between the sun and any object in space. This was, of course, solar radiation pressure, but he didn't know that back then. And it would take more than 200 years before Maxwell provided theoretical proof that indeed there is solar radiation pressure. Any object in space experiences this pressure from the sun. It would take another few decades before this was experimentally proven, and then another 20 years or so before the first person, Tsiolkovsky, another big name in space propulsion, rocket propulsion, astrodynamics, and Sander, that they came up with the first proposals for what we now know are solar sails. But still, it would take another 50 years, of course, for the whole space race to happen. That NASA was the first to propose an actual solar sail mission. And a nice detail is that this mission was supposed to go to Comet Halley, which was, of course, the comet that Kepler observed 400 years earlier, which started this whole story, this whole idea of solar sailing. Unfortunately, as very often due to budgetary reasons, political changes, this mission never happened, but it was the first time that a space agency really considered solar sailing as propulsion method for a mission. And then finally, in 2010, the first solar sail mission really flew. This is the Icarus mission by the Japanese Space Agency. And this is a real picture of the solar sail in space. I think it's one of the most beautiful selfies in space, because what actually happened is that there were two small cameras on board of the satellite. After the sail was deployed, these cameras were ejected. They turned around and they took a picture of the solar sail. So this is a real picture of the solar sail deployed in space. So let's start a new timeline. So the Icarus mission was the first one, as I said, by the Japanese Space Agency. It was launched together with a bigger satellite that was sent on a path towards Venus. So Icarus also went to Venus. And it showed that indeed this big sail, this structure, created a force on the satellite. Mass was about 300 kilograms of the whole satellite. And I now have a few quiz questions, this mission and also another mission, to give you a bit more sense again of dimensions and scales of solar sails. So, quiz question, how big, more or less, do you think the sail of the Icarus mission was or is? Is because it's still in an orbit around the sun. 1 by 1, 15 by 15, 30 by 30, 100 by 100. Just a guess. Oh, I wish the C's and D's were right and that we were already capable of building such big sails, but it's 15 by 15 square meters, the size more or less of a badminton court. Still, for the first solar sail in space, quite a nice achievement, and I hope yeah, at some point we will reach these values, but not quite there yet. The Japanese were kind of lucky because actually NASA was supposed to be the first ones to launch a solar sail in space. They built the NanoSail D mission. It was launched before Icarus, but unfortunately the launch failed and the satellite was lost. So they used the spare of the mission, called it NanoSail D2, and they launched it this time successfully just a few months after the Japanese mission. This satellite stayed in orbit around the Earth, did not go to Venus, and was also of a completely different dimension. So 4 kilograms, a so-called 3U CubeSat, that's more or less the size of a shoebox, with a sail smaller, about 3 by 3 square meters. Quiz question on a different dimension. How thick, approximately, do you think the sail of this mission was? Do you think it's thicker than 0.2 millimeters, which I can't even indicate? 0.2 millimeters, that's more or less the thickness of a sheet of paper. 40 to 100 micrometers, that's the thickness of a hair. I already see a hand raised. As thick as aluminum foil or tin foil, or even thinner than that. Thinner, I see thinner, even thinner. Anyone? Well, just shout, A, B, C, D, E. So, around this order of magnitude? Well, actually, the thinner one was right. It's even half of this, 7.5 micrometers thick. It's so, thick, actually thin. It's so thin, I once held a sample in between my fingers, and if you close your eyes, you still feel your fingerprints. It's so thin, you just don't realize there's anything in between your fingers. And then imagine that this is stowed, deployed, kept in tension, and it works more or less perfectly. So after the first 2 missions, it took a while before another mission was flown. This one is nice because it was launched by the Planetary Society, which is a private society, private organization. So it means that this mission was fully funded by donations and membership fees. It was a similar mission to NanoSail D2, similar dimensions, similar size of the sail. So we're talking about the size of more or less a loaf of bread, and the size of the sail of a boxing ring. They were so successful that a few years later, they launched another satellite. And this one was particularly nice because it was the first to really demonstrate that with a solar sail, you can do orbital maneuvering. You can put a satellite from one altitude, orbit with one altitude, into the next one. This is more or less what you see here. This is the evolution of the point on the orbit which is farthest away from the Earth. This one which is closest to the Earth, so it's a slightly elliptical orbit. But you see how the orbit maybe slightly pulsates. And this is due to the use of the solar sail, due to the force on the satellite by the solar sail. Then, last mission I would like to mention, there's one more, but one that has flown, or has been launched, I should say, is the Near-Earth Asteroid Scout mission, also by NASA. This one was particularly noteworthy because it would be the first scientific mission. All previous missions were technology demonstrators to show that we can store the sail, that we can deploy it, that a force is actually generated. This one was supposed to use the sail to really maneuver to an asteroid such that the satellite could take observations of the asteroid and send it back to Earth. However, as you can see here, it was launched in November on board of the, maybe you saw it in the news, the big SLS space launch system, the big new rocket of NASA with the Artemis mission on board that was sent on a trajectory towards the moon. This satellite was one of 10 little satellites that hitchhiked along with this bigger satellite, bigger mission, Artemis 1. But unfortunately, after it was deployed from the launcher, they couldn't establish communications, and they still haven't been able to do so. They'll try for a few more months, but if they can't, unfortunately, the mission is lost. So fingers crossed. And then, yeah, the one that I already mentioned earlier, the show, I showed the nice deployment video, is the ACS-3 mission. As I said, the size of 9 by 9 square meters. And this will test a new deployment mechanism. And I'm very lucky. The reason why I have the video is because I'm collaborating with the mission team, the PI of the principal investigator of the mission. I'm helping them to see how they should use the sail in orbit to change the orbit, but also to calibrate, to measure the force on the sail. So I'm very lucky to be in touch with them and to provide a small contribution to the mission. Now, you've seen a lot of solar sails over the past few slides. They all have different sizes, different masses of the satellite. So how can you really compare these different solar sails? Is bigger better, is smaller worse? So yeah, how to compare them? Now, this was the equation I showed you before. The force on the sail, twice the pressure, times area, times the cosine of the pitch angle squared. But when we talk about orbital dynamics, so the motion of a satellite with a solar sail in space, we're often not so much interested in the force, but actually the acceleration. So we divide by the mass. Well, the pressure from the sun is given. We can't change that, right? The attitude of the sail, it's given by the mission requirements. So the performance of the sail is fully determined by the area to mass ratio. The larger the sail and the smaller the mass, the better, or the larger the acceleration, and the better you can maneuver with the solar sail. So a bigger area in itself doesn't mean it's a better sail. If the mass is then much bigger as well, then maybe the performance is the same. So if I then plot kind of the mass of the different satellites and the area of the sails, then these are the missions that have already flown. Ideally, you're somewhere here in the bottom right corner, and you see that NEA Scout, the last mission that has been launched, is already moving in that direction. So technology is improving, and NEA Scout, ACS-3, the next mission will be a little bit even further to the right. So technology is improving, but we still have a long way to go. That kind of completes the first part of the presentation, a little bit the technical side of things. So if you like, we can have a short break for questions now. Yeah?
Yes. Okay. First, I want a big hand for Jeannette and her clear explanation. Jeannette, thank you very much for your clear explanation. You had very nice animations in your talk, which explained a lot of things. Are there any questions? Yes, there are many. I have some few, but I start here and then we will see where we end. Go ahead.
Okay, first of all, I'm not a physicist, so this is a simple question. You talked about momentum of a photon. I didn't get it.
Yeah, so I'm not a physicist either, right? So I can't tell you the details of the interaction between a photon. And now, of course, the two theories of light, massless and mass. But if you, of course, take the theory that a photon has a mass, then it also carries momentum. And then when it impacts on a surface, it transfers this momentum onto the object on which it imparts. But I can't tell you the two theories behind light. That's not. Yeah, but so there's a difference. So a solar sail does not work on solar wind. Solar wind indeed consists of high energy particles, ions, and things like that. These of course also impact on a sail, but the pressure of that, the force of that, is many times smaller than the force from solar radiation pressure. So a solar sail purely functions on the pressure of photons on the sail, not of the solar wind. So those are two different things. Yeah.
Okay.
Well, The solar cell will or does it ever get in the way of the communications? You mentioned this, but yeah, does it block the communications in any way or does it go right through?
Yeah.
Good question. Yep.
Yeah, no, so of course you can't just orient your sail in any direction at any point during the mission. There are some constraints, and one of those constraints could indeed be your communication, that your antenna needs to point towards Earth for communication, and then the sail cannot be in front of the antenna. And these constraints need to be taken into account whenever you design a mission or you do computations on the transfer of a satellite from A to B with a solar sail. So yes, yeah, it doesn't pass through the sail. No, that would be nice, but no.
Jeannette, could you say a little bit about the type of accelerations this whole configuration of such a satellite and a solar sail could get? I suppose it's very tiny accelerations.
You're talking millimeters per second squared.
Millimeters per second squared. So it takes a while to get into a higher or lower orbit if you want to use a solar sail.
Yeah.
Okay, no, good to know.
You are talking about photons. Is it only visible light we are experiencing here?
Yeah.
Or is there any other radiation coming from the sun which will influence force on the solar panels?
Yeah. So no, it's again, I'm not a physicist. So if there is anyone here and think I'm wrong, please correct me if I'm wrong. But it's of course the entire electromagnetic spectrum. But because we have the aluminum coating, it's kind of optimized for the visible part of the spectrum.
And why is it optimized for the visible spectrum?
That's indeed a very good question. Does anyone have the answer in the audience?
Are there any physicists? There's one in the back. The spectrum of the sun is mostly
in the visible
visible
part.
light.
Okay.
That's the reason, probably.
Okay. Yeah.
Yeah. Okay. Thanks. Good comment.
There are always fundamental questions, but I think, why
question?
didn't I? Yeah. Thank you. Thank you.
Okay. Here's the next question.
You mentioned at some point that by pitching the solar sail, we actually results in a decrease in the force applied to it. But isn't this the same force that allows us to switch orbits, like this orbital maneuverability that you mentioned?
Yeah.
So why would you consider that a disadvantage? That isn't it actually like an advantage? It's more flexible.
It's a disadvantage compared to other forms of propulsion. If you have a normal rocket or electric motor or on board of a satellite, it can thrust in any direction and it can thrust in any magnitude in any direction. A solar sail can only thrust at one magnitude in one direction, and this magnitude direction is very coupled. So maybe you want to thrust in I don't know, if the sun is there, you want to thrust in that direction, but actually you can't thrust at maximum magnitude because you're not going exactly opposite to the sun. So this is a disadvantage, and it might result into longer transfer times and things like that. So it's a disadvantage compared to traditional forms of propulsion where you don't have this constraint. Yeah?
Okay. Yeah. The neighbor. Go ahead.
Does this very thin material that the solar sail is made out of support like all the space dust that there is, in a way that it will travel for a long time?
Yeah. Yeah, good question. So indeed it might be that a micrometeorite hits the sail and causes a puncture or even a small rip in the sail. So what they do is they apply so-called rip stops. So kind of, an extra strip of material to prevent the rip from traveling further. So it stops the tear in the solar sail. This is what they do, but yes. So therefore, I hope I said it correctly during my presentation, that in theory, you can thrust forever, but there are effects like micrometeorites or effect that the optical coating degrades over time, which also puts a limited lifetime to a solar sail, but we're talking tens of years. So yeah, the sail will degrade over time.
Yeah. Okay. Go ahead.
Thank you for the nice presentation. I have a question about the predicted use of those solar sails. Can we expect them to be mainly useful in large space exploration for a couple of years or tens of years to explore everything? Or would we expect in the future GPS satellites to be solar sail propelled because they last longer in that way?
Yeah. So I will go into some applications, typical applications of solar sails in the second part of the presentation. But in general, the type of missions you should think about is missions that require a huge buildup of velocity. For example, and this is not an application I'll mention later, but with a solar sail you could visit maybe 12, 15, 20 asteroids with traditional forms of propulsion, a rocket-based propulsion. You can maybe visit one or two, but then you run out of propellant. So very long duration missions and also missions that require a lot of changes in the orbit of the satellite, need a huge increase in the velocity, so you build up acceleration and velocity over time. But I'll go into some specific examples in the second part. If you then still have questions, feel free to ask again.
I go here, and then we come down. Yes, go ahead.
Thank you for a nice presentation. I can imagine that these solar sails, in the future, you want to continuously change the angle of attack, so to say, of the solar sail. But I'm having trouble wrapping my mind around how that would work, because you're not fixed to anything, which you have additional actuators, such as microtrusters or so.
Yeah, so there are different ways of steering the sail. Can be either by kind of electromotors, but it can also be with tiny, so if you have this square sail, you have these 4 booms, that you put tiny vanes at the end of these booms, that you can articulate the vanes, and because the vanes are far away from the center of mass, they create a relatively large torque or momentum, and in that way you can also change. There are different ways of changing the attitude of the sail, and as long as you do that through a way that if you need electricity or power for that, you do that through power generated from the sun, then this will not be a limiting effect on the lifetime of the mission. But yeah, there are different ways of doing that. Yeah.
Okay. One more question, and then shall we
Sure,
go to the
yeah.
applications? Yeah.
I have the same question.
You have the same question. That's a coincidence. Okay. Jeannette, shall we continue with the very exciting applications of this whole solar sailing technology?
Yes. So, solar sailing, the technology, the orbital dynamics of it, that's, that's what captivates me. But that's only one part of the story. I don't want to just do nice calculations and simulations for the fun of it. I really want to try to show how solar sails can enable missions that will really help with some of the big problems we are experiencing here on Earth or even in space. So I will go through 5 what I think are, relevant, important applications. The first 2 I'll discuss in a bit more detail, and the third and the 3, 4, 5 in a little bit less detail. The last one, interstellar travel, is maybe not something that we need right away, but I think it's nice to end with a sort of futuristic outlook of solar sailing. So I'll first talk about space debris removal, then geoengineering, space weather warning, planetary protection, that means protection from astronauts, and then interstellar travel. So first, space debris removal. If you look on the website of the European Space Agency, of the Space Debris Office, somewhere you will find this quote: "There's a problem brewing overhead, and this problem is called space debris." There are there really are millions of pieces of debris floating around the Earth, and debris consists of old satellites that no longer function, parts of rocket bodies, upper stages of rockets, fragments of satellites that for whatever reason have broken up. And if they are from millimeter scale, then we're talking about millions of pieces, to full satellite scale, as big as a bus. There are fewer of those, maybe a few thousand, but still the numbers are staggering. And considering that through all this mess, there are satellites orbiting the Earth that we rely on for, as I showed at the start of the presentation, navigation, communication, security, and so on. And both the debris and the satellites, they move at very high speeds, which means that if even the tiniest piece of debris, centimeter squared, hits the satellite in the wrong place, in the computer or the instrument that observes something, then the satellite is lost. But it's not just functional satellites, it's also astronauts on board of the International Space Station. So this is just one example, but for example, in the last quarter of 2021, and if I were to update these numbers for sure, I would find the same in 2022, the International Space Station had to conduct 2 maneuvers to prevent a potential collision with a piece of debris. So we're talking about the safety of astronauts on board of the International Space Station. So the global space community agrees we need to clean up space in order to preserve the near-Earth environment for future generations. If we don't do anything about it, there will be more and more and more and more debris. And within 20, 30, 40 years, there's just too much debris to even launch a satellite or for satellites to safely orbit around the Earth. Now, there's a proposal from ESA, or actually a mission has been commissioned by ESA. It's called Clear Space 1, which will launch one satellite to maneuver to one piece of debris, to grab it, and to bring it down to a lower orbit where the atmosphere will eventually burn up both the satellite and the piece of debris. Now, launching one satellite to remove one piece of debris, considering that there are thousands of pieces of debris out there, I don't think is the most sustainable or cost-effective solution. So what I proposed is, can't we use a solar sail to do something similar, but in a more efficient way? You use the sail to go to a piece of debris, you grab it, and the sail then brings the piece of debris down towards the atmosphere, releases it, and the sail is then used to go to the next piece of debris. And because, and the story is the same every time, there's no reliance on a finite amount of propellant on board of the satellite, so you can continue doing this until the sail itself, through the micrometeoroids or other effects, degrades to such an extent that it's not used anymore. So I believe that compared to other proposals out there, this is a much more cost-effective and environmentally sustainable solution because, again, it's the only form of fuel-free propulsion. And I think it's the only way to remove many pieces of debris with a single satellite. Now, I pitched this idea to the Dutch Research Council and WO for a so-called VD grant. I don't know if you're familiar with it. And they liked it, so they awarded my proposal. The proposal is called Sweep Space Waste Elimination Around Earth by Photon Propulsion. And it's a 5-year project. And within those 5 years, we will answer the question, can a satellite with a solar cell actually move towards a piece of debris, deorbit them, and repeat this cycle? And you might think, well, haven't you figured that out already? Well, 95, if not more, % of all the literature out there that looks into the motion of solar sails is in interplanetary space, far away from the Earth. We know very little about how a satellite with a solar sail moves around the Earth. Dynamics are far more complex. So what we will do, and with we, I mean myself and 2 PhD students, is we will hopefully unravel the solar cell orbital dynamics around Earth. So we will investigate the motion of a solar sail around Earth, how to use the sail to go to a piece of debris as quickly as possible, to bring it down towards the atmosphere as quickly as possible. But also the question, with hundreds or thousands of pieces of debris that you would like to remove, which pieces of debris should we remove in which order? And this is basically a huge traveling salesman problem. I will not do this by myself. Thank goodness I have the support also from a big network. This is just to indicate that solar sailing is not something, again, futuristic, something that is under investigation in many institutions, universities, companies, space agencies, and particularly the application of space debris makes it very, very interesting, tantalizing, and important. So NASA is involved, ESA, and also some universities around the world, or at least in Europe and the US. So that's one application. The other is something completely different, and is application related to geoengineering. Now, I heard you already had a lecture about geoengineering. Maybe I don't need to tell you what it is, but for those of you who missed that lecture or can use a reminder, geoengineering is the deliberate large-scale manipulation of an environmental process that affects the Earth's climate in an attempt to counteract the effects of global warming. And this basically means that we use engineering to counteract the results of global warming. And it's very important to note here that no one who's working on geoengineering would want this. The thing is that we are so not doing well in terms of reducing our carbon dioxide emissions that we are facing some very severe consequences of climate change. We already see them: floods, fires, droughts, and so on. And the use of geoengineering is only meant to kind of remove the worst effects until we have our CO2 emissions under control. So again, it's important that this is not as a solution, oh, we'll implement this, we'll do this, and we can just continue with our CO2 emissions. No, it's only until we have our CO2 emissions under control. So that's geoengineering. When you talk about space-based geoengineering, you're talking about what are called sunshades, where we basically use a large shield or a shade to block a little bit of sunlight that will then not hit Earth, and therefore the temperature on Earth will be halted or decreased. Now, a little bit of introduction into geoengineering. There are many different ways. These sunshades are just one of them, but they can basically be categorized into two categories. One is carbon dioxide removal, where we actively remove CO2 from the atmosphere and store it either in the ocean or the soil or in some storage facility. The other category works on solar radiation management. So as it says, reducing the solar radiation absorbed by the Earth. Those are kind of the blue squares here. So that's what a sunshade is also about. So let's have a closer look at those methods. So you can limit the solar radiation absorbed by Earth either by, for example, enhancing the Earth's reflectivity on land. So, for example, painting the desert white or using certain crops. You can also do it in the air by whitening clouds or using aerosols. And then finally, completely detached from the Earth, we have the sunshades, where again, where we limit the amount of sunlight that even reaches the Earth. And that's what we call space-based geoengineering. So how does it work? So this is basically the concept. We have the sun here, of course, we have the Earth here, and we place the sunshade, which is basically a solar sail, between the sun and the Earth. Now, immediately behind the shade or the shield or the solar sail, there's what we call umbra. It's complete darkness, a full shadow. There's no sunlight there. There's also a big region behind the shade, which we call penumbra, where we have partial shading. So basically, and that's where the Earth would be. So basically, if we look from the Earth towards the sun, and this is not to scale, but this is what you would see. Don't look at the sun, of course, but if you could, this is what you would see. So the sun shade would cover a tiny part of the sun. And scientists, climate scientists, believe that if we shade it by 1 to 2%, so block 1 to 2% of sunlight, we can avert or stay away from the worst effects of climate change. Now, where my work kind of comes in is where do we place such a sun shield? And for that, I'll give you another tiny introduction to astrodynamics. So if we have the sun here and the Earth moves around the sun, then an object that orbits the sun closer will orbit around the sun faster, right? Venus is closer to the sun, has a higher velocity, orbits the sun quicker than the Earth. And the opposite holds for any object orbiting around the sun further away from the Earth. Mars orbits at a slower speed than the Earth. Now there are multiple, but one particular exception to this rule. There is one location between the sun and the Earth where the gravitational forces and centrifugal forces work out in such a way that actually at that point you orbit around the sun at exactly the same speed as the Earth. And this point is called the L1 point, the Lagrange point L1. It's at approximately 1.5 million kilometers from Earth. It's about 4 times the distance from the Earth to the Moon. And this is the perfect location for such a sun shield because then it will always be between the sun and the Earth and can continuously 24/7 shield that 1 to 2% of solar radiation. Now, some work that I didn't do, but just to give you an idea, what would be the effect on the climate? So this is work by Pau Sanchez and Colin McInnes. This was my PhD supervisor, one of the big names in solar sailing. This is a current collaborator of mine. They conducted this study a few years ago where they placed, yes, it's a huge number, but they placed a sail the size of 1,400 kilometers at this L1 point. And they did a climate simulation where they assumed that the atmosphere would contain twice the CO2 levels as it did in 1980. And they simulated the climate with and without the sunshade for 50 years, because after 50 years, we can assume that the climate has once again reached an equilibrium. On the left, you see the effect on the temperature increase on Earth without a shade, and on the right with a shade. And important is to note the difference in color scales. One goes up to 6 degrees with a sunshade. It only goes up by 1.5 degrees. So this is an indication that a sun shield could potentially work. However, there's still work to be done. You see there are regional variations, much more increase on the poles, which you don't want, melting ice, things like that. So you could think about a moving shade that shades the poles a bit more than the equators, or a constellation of shades. And this is work that we are currently collaboratively working on. I also supervised a study of a project of a group of students for their final project of their bachelor's at our Faculty of Aerospace Engineering. It's a big project. It's 10 students working together for 11 weeks full-time. So this is a serious amount of effort that they put into it. And they were asked to design a mission which was defined by OHB, which is one of the biggest satellite builders, constructors of Europe. And they were tasked to design a mission similar, a sunshade at L1 that would block up to 2% of sunlight. They had a budget of $1 trillion US dollars. I don't know if that means anything to anyone. I mean, it's a ridiculous amount of money. It's about 5 times the entire budget of the Apollo program of NASA in the 1960s and 70s. Operational lifetime 20 years, and it should commence in 2031. They worked for 11 weeks, and they indeed designed a mission. This is what one of the many, and I'll show you the numbers later, sunshades would look like. So it would be a big solar sail wrapped around the satellite, and by spinning up the satellite, the sail or the shade would deploy. Now, based on the absolute maximum mass that you could launch with the most realistic future rocket, one of the new rockets of SpaceX, you could maximum launch a shade with a diameter of 5.4 kilometers radius. But to block 2% of sunlight, such a shade is not enough. You actually need 70,000 of these spacecraft. They also looked at the cost, and I'm not going to go into detail of all of this. The only thing I want to show you is that with a mission like this, only a relatively small portion of the cost actually goes into the spacecraft. You have huge launch cost, operational cost, facilities, because where on earth do you house, test, build such a huge solar sail? But in the end, they managed to keep it more or less within $1 trillion. So this is just to show that, you know, we are working on this, but we're still at the very first baby steps, trying to get an idea of what magnitude, scales, cost are we talking about. Because, of course, it's also important to then be realistic and be objective about, okay, sunshades are one way of doing this. If we want to do this whole geoengineering thing, are sunshades the best choice? So to compare different geoengineering techniques, there are 4 criteria that are often used. The first one is effectiveness. How well can the whatever measure you put in place control the temperature increase? And the higher up this vertical axis, the more effective. Timeliness. How quickly can we deploy the technique? It's given by the size of the dot. The bigger, the quicker we can deploy. Safety to the environment and the population. Red dots, not safe. Green dots, very safe. And finally, cost or affordability. So the further up this horizontal axis, the more affordable the technique. Now, if you then look for the space reflector, it's called here, or the sunshade or the space shield, you see it's right over there. It's very effective. You can very well, in a very good way, control the amount of solar radiation that hits the Earth. It's also disconnected from the Earth, so you really only block solar radiation. There's no other interference with the Earth's climate. You can also, if you don't need it anymore, very easily remove it. However, timeliness, not so good. And I'll show you later, if you want to launch 70,000 satellites, it takes a while, not just to build, but also to launch.
Excuse me, is it low affordability or low cost?
No, so this is low cost, high cost. So the further to the left on the horizontal axis, the higher the cost. Yeah, it's a bit counterintuitive, I agree. But it's rather safe because, again, it's disconnected. It's the only technique that's fully disconnected from the Earth. There's no interference with any infrastructure. You can easily remove it if you don't need it anymore, if there are side effects that you weren't counting on. And the cost, well, I already showed you. It's not very good in terms of cost. So there are still some challenges to overcome when it comes to space or sunshades. I already mentioned we'll probably need something in the order of thousands of satellites. If you then look in 2021, only 1,300 satellites were launched by anyone on Earth. So even if we were to launch 70,000 per year, so if we were to start launching today, 7,000 sunshades every year, SpaceX only conducted 25 launches in, well, in this case 2020, but something similar in 2021, 2022. I already mentioned the size of such a sunshade is enormous, so where do you test something like this? Where do you build this? The largest sail built to date is the 100 square meters, more or less, from the Icarus mission, and so on. Also on the climate side of things, you know, we know quite well what the global response is, but regional responses or responses in terms of precipitation patterns, not so much. And also a sunshade doesn't provide solutions to other effects of greenhouse gases like ocean acidification. But then there are also, and I'm just going through all of this to be realistic and objective, right? There are other challenges, social, political, legal. Do we want this as a society? Can you do it even politically or economically? Who's going to fund it? $1 trillion. You have to then also look at what are the costs of climate change, which are actually far higher than the $1 trillion. How to get public support if this were ever needed. Well, if you look at research, many of these questions remain unanswered. So, Pau Sanchez, that I mentioned before, and we wrote a big proposal that we submitted to the European Union for 2.5 million euros for 10 PhDs to investigate all of this in an interdisciplinary way. The technology, that's where I come in, the economics, the ethics, the legal side of things, the climate side of things, in order to do an objective study to say what can be done and what cannot be done. Are sunshades really a realistic option or not? It's well possible that if this is awarded, we'll know in April, that after 4 years of study, we'll have to conclude that no, this is not workable or desirable or achievable. Still means that all the work is done can be applied in different ways, in different fields, so the 2.5 million will never be, let's say, lost. But we need to provide answers, not just for sunshades, but also for the other geoengineering techniques. We need to provide answers to all these questions before we can even start thinking about implementing it. So those were kind of the two more lengthy applications that I wanted to mention. I have 3 more, but I'll go a bit more quick through those. So one of the applications that has been proposed for solar sails already for many, many years is to use them to warn for what are called solar storms. So solar storms are huge outbursts of basically solar wind, but in extreme ways, huge outbursts of high particle radiation by the sun. And under normal circumstances, the magnetic field of the Earth shields us from that harmful radiation. But if the storm is really powerful, it can enter the magnetic field and can have some severe effects. A good effect, a beautiful effect, are the northern lights. Desirable, beautiful, but they can also cause power outages, health risks, of course, to astronauts, damage even to oil pipelines. So ideally, we want to know that such a storm is coming. And we can do that. We're already doing that by exploiting this L1 point that I talked about previously in this slide. This point between the sun and the Earth where a satellite moves around the sun at the same speed of the Earth. We currently have 4 satellites, SOHO, ACE, WIND, and DISCOVER, at the L1 point that observe the sun. And they also detect whenever a solar storm passes by the L1 point. There are detectors on board of those satellites, and they detect an increase in solar radiation. And they then send a warning to Earth so that operators of power grids can shut down power grids to prevent damage. Satellites can turn their instruments away from the sun to prevent damage, and so on. Now, because the warning signal towards Earth travels at the speed of light and the solar storm travels slower, there's about half an hour between the warning arriving on Earth and the solar storm impacting on Earth. This is, of course, not a lot of time to shut down power grids and so on. So ideally, you want to increase this warning time. And that's where a solar sail comes in. Because with a solar sail, you can exploit the force on the sail to artificially move this point towards the sun. You are then closer to the sun, still orbiting at the same speed as the Earth, but you can detect the storm sooner. And therefore, the warning time goes up from half an hour to 1 hour. Still not a lot, but it's an increase or doubling of the warning time. And this is considered very important by operators, again, of power grids, aviation, and so on. This would have been the destination of NASA's Sunjammer mission, but unfortunately, again, budget, politics, this mission was cancelled, but recently a new mission has been proposed, Solar Cruiser, which will hopefully indeed use a solar sail to artificially shift this wonderful point that we can exploit towards the sun and show that, for example, we can increase the warning time for solar storms. Another application that is closely related to this is planetary protection or warning for astronauts that are heading towards asteroids that are headed towards Earth. This seems like a very sci-fi Armageddon type picture, but you might know that this is actually real, right? In 2013, a big meteorite entered over the over the skies over Chelyabinsk in Russia. And it wasn't so much the meteorite itself that caused destruction. It enters at such a high speed, it creates a shock wave, and therefore windows were shattered in buildings over, I believe, a 10-kilometer radius. And people saw a flash of light in the sky. They all went to the window to look at what's happening there. And then the shock wave arrived, glass shattered. So there were a lot of injuries due to this. So again, you want to know that an asteroid like this or a meteorite like this is coming Earth's way. They didn't know that this one was coming, and the reason was that it was approaching the Earth from the direction of the sun. And I was joking earlier, don't look into the sun. But this is a real thing. We can't look in the direction of the sun. There are a lot of telescopes on Earth that continuously scan the sky to find new asteroids, new meteoroids that have not been detected so far. But they can't look, more or less, in this exclusion zone towards the sun. And again, that's exactly what happened with this Chelyabinsk meteorite. It approached the Earth through this exclusion zone and was not observed. Now, again, by using that, putting a satellite at this Lagrange point, you can make this exclusion zone not so much smaller, but you can shift it such that you actually could have observed the asteroid already here and along its path here. Maybe you would have had a few hours maximum. If again you use a solar sail and shift this point towards the sun, you can detect the asteroid again much sooner on its path towards the Earth. Finally, the last application, maybe a bit more futuristic one, but I think it's a nice one to end the presentation. For years, decades, many people on Earth have been dreaming about going to Alpha Centauri. That's our closest neighboring star system. Alpha Centauri is about 4.4 light years away from the Earth or the Sun. Doesn't really matter on those scales. I don't know if you know how big a light year is, but this is kind of the distance in kilometers. It's huge. The furthest object in space that was sent by humankind Voyager 1. Voyager 1, not 2, 1, was launched in the 1970s and is still moving away from the Earth, from the Sun. But after all those years, it has traveled only 0.0023 light years. It would take another 2,000 years or so, or even more, for Voyager to get anywhere close to Alpha Centauri. And this will be the case for any satellite that is propelled by normal forms of propulsion, rockets, and so on. You can't build up enough velocity, energy, to escape from the solar system quick enough to travel to Alpha Centauri quick enough. And again, that's where a solar sail comes in, because we talked about solar radiation pressure and its magnitude. At Earth's distance, it's extremely small. The closer you go towards the sun, the bigger it gets. And therefore, also, the bigger the force on the sail gets. So what you can do is you can steer the solar sail to do a very close pass of the sun. Then the force on the sail is so huge that it will actually throw the satellite out of the solar system. Then you're talking about travel times of maybe a few hundreds of years. There is an initiative called Breakthrough Initiatives. I don't know if you've heard about it, but they are proposing something even more advanced, futuristic, not sure what the right word is. But to increase the pressure on the sails even more, they are proposing to use lasers to propel the sail forward. They propose to put a big laser array on Earth that shines on the solar sails, and with that, they hope to be able to reach Alpha Centauri in only 80 years or so within a generation. There's real work going on this. We'll have to see if it ever happens, if these lasers can be built, if those kind of sails can be built. But who knows? We'll see if maybe in 30, 40, 50 years or so, the first solar sail towards Alpha Centauri is launched. I won't be able to witness its arrival, but it would be a nice idea that one day we will indeed get there. And with that, I would like to end my presentation. Thank you very much for your attention. And if you have any further questions, then please feel free.
Thank you, Jeannette, for this fascinating second part of your lecture. It's really dazzling a little bit, but it was really, really interesting. We have I think 5 minutes left for the public questions, and then you will be here afterwards.
Yes.
You're staying in the hotel,
yes.
so you don't have to hurry back to Delft, so you can always ask your question informally afterwards. But perhaps there are questions already, very urgent.
Thank you for the presentation. I have a question about the sail and the debris, the space debris, because as it approaches debris, probably is also more possibility of it getting hit.
Yeah.
How will you deal with that? Maybe?
Yeah, so this is something we need to investigate. It's never been investigated before, researched before. So indeed, part of the work that has been defined is to investigate the interaction between the sail and the piece of debris itself. You could also maybe have a tumbling piece of debris. So when you connect the sail, you need to first use the sail to detumble it, stabilize it. This is all part of the work we will execute. So yeah, it's a question I don't have the answer to yet, but it is research that we will carry out. Yeah.
Mm-hmm. Jeannette, can you give an estimation? How long will it take to get a piece of debris and then bring it down to a lower orbit with these? You talked about the accelerations of about millimeters per square second. So how long does it take? What?
Yeah, it very much depends on the piece of debris,
yes,
of course.
Yeah.
If it's a tiny piece, you can maybe do it in estimate 40 days, 50 days.
Okay.
The bigger it gets, the smaller the acceleration, the longer it will take.
Yes.
So for maybe a huge piece of debris, it might take a year. to get it down.
Aha.
But the
Okay.
exact numbers I will be able to give you in 2-3 years time.
Yes, yeah, but you have to be very patient.
But
to-
those are
to
the
clean-
orders of magnitude.
Yes,
It's
okay.
not done in a day.
No, exactly. That's
yeah.
what I wanted to hear, or what I try to understand. Thank you.
Thank you very much for the presentation. It was really interesting. When using the solar sail specifically for combating climate change, do you think we are still in time to develop it, to build it, and to use it
Yeah.
in order to effectively combat it?
Yeah. So, what I think, again, if this is ever implemented, I don't think it will be a matter of using just one technique. I think it will be a combination of techniques. It might be sunshades with aerosols, with whitening the desert, I don't know. And in that case, of course, the amount of sunlight, it's also to spread the risk, you know, and the side effects of each technique. And in that case, you're talking about far fewer satellites that you would have to launch. The technology is there. It's basically it's basically a solar sail. They have flown, so you could build it today and launch it and start building up a sunshade. But to create a full sunshade of this 1,000, you know, size diameter, that will probably take 30 years. And then, of course, it depends on how bad we are in decreasing our CO2 levels, whether we are on time or not. If it's a combination of techniques, I think it's doable. If it's going to be the only technique, and we continue as society as we are, we might be too late. I think we have a few more years, after which we kind of missed, you know, the window of opportunity is gone. But I'm not a climate scientist, but this is what I, of course, read in articles from climate scientists. Sorry. Yeah.
Yeah. Okay. Thanks. Go ahead.
Thank you again for the presentation. We were talking before about moving the Lagrange point, but isn't this proportional to the area of the solar sail? I mean, we cannot get the Lagrange point wherever we want because the solar particles would propulse the solar sail in a directional opposite to the Earth, and we need to cancel, because of the cancellation of gravities between both planets, we need to also counteract the motion from the sail.
Yeah. Yeah. So if I understand your question correctly, and hopefully this is the answer to the question. So if we have the sun, we have the Lagrange point, and we have the Earth. Basically, you are right that the force on the sail acts in that direction towards the Earth. But it basically means that we kind of reduce the solar gravity a little bit.
It's true.
Yeah, which means that the solar gravity is reduced a little bit, and therefore this point shifts towards the sun.
It's true, but that's proportional to the area of the solar.
Oh, so yeah, it's sorry, then I understand. Yeah, the shift depends on the area to mass ratio.
So we cannot actually see it as much as we want because we cannot build a high.
No, you
big
can't.
enough.
You can't. No, with current technology, you can. You can shift this L1 point by the same amount as the distance between Earth and L1. So you can double the distance between Earth and this. So Earth L1 is 1.5 million kilometers. Earth between the shifted L1 point is about 3 million kilometers with current technology. Yeah. Those
Okay.
were all schematics, of course, not to scale. Yeah.
Yeah, thank you for the presentation. It was very interesting. I would like to ask something else that it might be a bit far-fetched, but this debris cloud orbiting like the Earth, isn't it in its own way like a form of sunshade? Because at least from the simulation, it seemed quite dense.
Yes, but well, yeah. So the simulation is realistic, but of course they put a dot for every piece of debris, but this dot is not to scale to the Earth. So the density of this cloud is far less than what you see in this simulation. And it's not not the best cloud to create, I would say. But if it would be dense enough, yes, it would be a sunshade in itself. Yes, yes.
Yeah.
Yeah.
Okay, Jeannette, we are going to round off.
Yes.
I was wondering, do you have a special origami department at the TU Delft? Because this folding
Yeah.
from such a tiny milk package into it must be very cleverly done, because otherwise it will end up like a mess.
No, so we in our department or faculty don't work on this, but there are people, their prime research is about this folding. And it takes, so I know the person who actually fabricates and folds the sail of the ACS-3 mission, and it takes a full week to fold the 4 quadrants of the sail. And they need to do multiple tests before the satellite is launched. So she has already spent months just folding the sail, yes. And it needs to be done very precisely, because if you do it wrong, it doesn't fit or it doesn't deploy right. So it's a huge responsibility. So it sounds fun, but it's a huge responsibility.
It doesn't sound like fun to me. So if you make one mistake, you end up and you have to unfold it again, and it's very, very complicated. I saw some more questions. Please come down and ask them to Jeannette here downstairs. Jeannette Heiligers, thank you very much for your inspiring lecture. We had the technical part and the applications part, which was very, very exciting. You told many, many things. One I wrote down was Kepler and his heavenly breezes, already in 1607. That's fascinating. You saw the tail of the comet being blown away by the sun, the solar, the photons. And I wish you very good luck with your 2 very important projects, the SWEEP project, so cleaning the space debris, and of course the climate engineering project, which is also very exciting. And I have one suggestion for the TU Delft logo to end with, because here I see some kind of fossil fuel flame. Can there be something like a sun or something on top of it? I think that would be better and more sustainable.
I'll communicate your suggestions.
I want a very big hand for Jeannette Heiligers.
Thank you.
Dank je wel.